In this section, I'll go over some of the problems on buffer solutions. Now, whenever you have a buffer solution, I already mentioned to you what is the composition of a buffer solution. Like you may have a weak acid and its conjugate base, or weak base and its conjugate acid. You must have a mixture of both in order to have a buffer solution. Now let's assume that you have a buffer solution. How would you calculate pH? The best way to get pH would be by using this expression, and this is called Henderson-Hasselbalch equation. pKa is minus log of Ka. So let me write down that. Minus log of Ka. And you know that there are two different logs. So this is log with respect to base 10. And log x minus by hx. X minus represents conjugate base and hx represents conjugate acid. As you can see, that there is a difference of H, having H or not having H. Here we are going to do a problem from the book, which is number 21A and page 742. So basically they gave you a mixture of lactic acid and sodium lactate. So obviously you have a lactic acid, which is a weak acid. How do I know that it's a weak acid? Well, I need to know the strong acids. There are not too many strong acids like HCl, HBr, HI, HNO3. These are the strong acids. Anything other than that would be weak acid. This is an organic acid, and in yogurt you'd have this acid because milk has lactose, and that changes into lactic acid. Anyway, so lactic acid is a weak acid, and I'm writing down the formula as HX. This is just a symbolic way of writing down. Then sodium lactate is a sodium compound of lactic acid. Now sodium, any kind of compound where sodium is bonded, sodium gets separated. So basically lactate ion, or X minus, is going to be in the solution. So you'd have lactic acid HX as well as X minus in the solution. In other words, this is going to be a buffer solution, and we need to do a calculation to get the pH. Now from back of the book, from appendix D on page 1062, I can find Ka value for lactic acid. So Ka for lactic acid equals to 1.4 times 10 to the negative 4. So that's the value I got from appendix D. Make sure you have the habit of looking at this appendix and double check my value. Now, in order to get pH, I'm going to just plug in my number in that expression. So keep in mind, from sodium lactate, you're going to get lactate ion, which would be 0.11 because sodium gets separated from lactate ion. So it'd be 1 and 1. So let me write down like this so that you understand it. NaX would get separated into Na plus and X minus. So if I have 0.11 molar, when it breaks down 100%, you get 0.11 of sodium plus. I don't care for that one. And I get 0.11 of lactate ion. That's what is important for me. So let's now plug in the numbers. pH equals to pKa, which is minus log of, we already know the Ka value, 1.4 times 10 to the negative 4, that's pKa, plus log of conjugate base concentration, which is X minus concentration, which is 0.11, divided by conjugate acid, which is lactic acid, 0.12. So now I got the setup, and that gives me 3.85 minus 0.0 378, and that gives me 3.81. So the pH of this buffer solution is 3.81. Make sure you redo this problem without looking at how I did it. And you make sure you understand every step of this calculation. Now we're going to do number 22 and A. This is, in this problem you have 0.105 molar sodium bicarbonate and 0.125 molar sodium carbonate. Again, this is a sodium compound, so in solution sodium would be completely gone. So you'd be, from the first compound, you'd be left with HCO3 minus, which would be 0.105, because 0.105 of sodium bicarbonate. Let me show you this step so that in the future you'd have understanding. It breaks down into sodium plus and HCO3 minus. And so if I have 0.105, so when it breaks down, it would be 0 left here. And then you would have 0.105 of sodium plus, which we don't really worry about. And then HCO3 minus would be 0.105. Now in this case, 0.105 of HCO3 minus would be important, because look at the other compound, sodium carbonate. Now Na2CO3, this will break down into, again, this is sodium compound, 100% sodium will get separated from the rest of the molecule. So you get CO3, 2 minus. So sodium carbonate, you have 0.125, and it would completely break down. So you get about 2 times of that of sodium plus, and same quantity of CO3 2 minus. So we'd have about 0.125 molar carbonate. That's what we are interested in. So here you can see that HCO3 minus, if you look at these two species, let me highlight this. HCO3 minus and CO3 2 minus, these are conjugate acid base pair. So from these we get HCO3 minus and CO3 2 minus. So this is, first one is an acid, is acting as an acid, and second one is this conjugate base, because you get the second species just by removing H plus from HCO3 minus. So now we can apply Henderson-Hasselbalch expression. And also something else I need to point out to you, I need a Ka value. So let me write down first Henderson-Hasselbalch expression. pH equals to pKa plus log of conjugate base by conjugate acid. Okay, now question is which Ka value I should have, because if you look at the back of the book, carbonic acid has 2 acid dissociation constant. So, and you in the back of the book you'd have values for carbonic acid. So if you have carbonic acid, in the first step it would look like this. Let me write down those 2 steps of reaction for carbonic acid. H2CO3 in first step would give H plus and HCO3 minus, and that's Ka1. In second step, HCO3 minus is going to break down into H plus and CO3 2 minus, that's Ka2. In this case we're dealing with HCO3 and CO3 2 minus. Obviously we're interested in Ka2. So I'm going to now write down, instead of pKa, I'd write down pK2 for carbonic acid for H2CO3. Let's write down in parentheses H2CO3. So Ka2 involve HCO3 minus breaking down into H plus and CO3 2 minus, and that's the value you're going to use, and that'll be minus log of pKa2, so minus log of, and I got that value from Appendix D, and that value is 5.6 times 10 to the power minus 11. It's a good idea to double check my values. So this would give me log of x minus is CO3 2 minus, and we already know that value, which is 0.125, and then at the bottom I would have hx, so let's write down that hx would be 0.105. In case you're confused, let me identify these. Conjugate base is CO3 2 minus, and conjugate acid is, in this case, HCO3 minus. And I just plugged in the concentrations of those that we know. For CO3 2 minus, I have 0.125, and for HCO3 minus, I have 0.105. Let me circle these. So when I do the math, what I get is 10.33. So pH of this buffer solution is 10.33. We are going to do number 27A. This is again a buffer calculation, pH calculation of 0.1 molar acetic acid and 0.13 molar sodium acetate. Again, by looking at Appendix D, we find out that Ka for acetic acid, and we are writing down acid as Hx. So Hx is 1.8 times 10 to the negative 5. 1.8 times 10 to the negative 5 is from Appendix D, page 1062. So you need this value, Ka, in order to calculate pKa. Keep in mind, whenever there is a buffer solution, you can always use Henderson-Hasselbalch expression. Now we need to find out X minus and Hx. These are conjugate acid-base pair. Obviously, acetic acid is Hx, so let's write down Hx, which is equals to 0.10 molar. X minus is acetate. Remember, sodium acetate, you add as a salt, because you can't just add acetate ion. So sodium salt would break down 100%, and it would have acetate ion in the solution. And I don't need to show you this equation again, sodium acetate, how it breaks down into acetate. So from the last slide, I think you probably understood this, and I'm just writing down the value, because 0.13 molar sodium acetate would give you 0.13 molar sodium plus and 0.13 molar acetate ion. So now let's plug in all these numbers. So we'd have pH equals to pKa, which is minus log of Ka, in this case Ka for acetic acid, plus log of conjugate base on the top, which is 0.13, and conjugate acid on the bottom, 0.10, and this is minus log of 1.8 times 10 to the negative 5 plus log of 0.13 over 0.10. Okay, and my first part I get 4.74. You can always double check. It's a good idea to do a calculations when I'm doing it. And from second part, I'm getting, for the second part, I'm getting 0.114. So this gives me 4.85. And I'm rounding off. So pH for this buffer solution is 4.85. Now we're going to do number 27b. We have done part A in previous slide. So this is number 27b we're going to do. So you have a buffer solution of 0.1 molar acetic acid and 0.13 molar sodium acetate. Question is, what's going to be the pH of the buffer solution after you add 0.02 moles per liter of potassium hydroxide? Now, in order to solve this problem, I need Ka value, and the acid involved here is acetic acid. So from back of the book, I got this number from Appendix D. So let's write down here Ka for acetic acid. And here we're writing down acetic acid as HX. So Ka for HX equals to 1.8 times 10 to the negative 5. So that's Ka value. In addition to that, we also know the concentration of HX before adding KOH. So before adding KOH, you'd have concentration of HX. That's equal to 0.10. And then X minus, which is acetate, is 0.13. 13 molar. This is before we add potassium hydroxide. Now let me show you first the reaction between potassium hydroxide and acetic acid. So we're going to write down symbolically HX for acetic acid. So let's write down the reaction. HX plus OH minus, that gives, now OH minus is coming from potassium hydroxide. Again, potassium gets separated from 0.02 KOH, we do get 0.02 OH minus. We don't worry about K plus because it's not taking part in the reaction. So that's why we're just writing down 0.02. So let's write down 0.02. And initial means before you added hydroxide ion, potassium hydroxide ion, you had initial concentration of HX as 0.10 is the concentration of HX or acetic acid before it had a chance to react with OH minus. Then OH minus with HX gives you X minus and H2O. You can see here HX, as H plus reacts with OH minus, you get H2O, then X minus gets separated. Now initially X minus was not 0. You can see on the right side, let me show you in red. Initially you had 0.13 molar. Because that was added. Remember, sodium acetate was added, and that's sodium's, when sodium gets separated, then you get 0.13 molar acetate ion. So you already have acetate ion, and water is in excess. This is a solvent. So at equilibrium means when you allow OH minus to react, 0.02 molar OH minus is going to react with HX. And how much will be left over? So 0.10 minus 0.02. So that's going to be the leftover of acetic acid or HX, which is 0.08. So 0.08 is the new concentration of HX. OH minus will be completely gone, so it'll be 0. for OH minus. X minus, remember when 0.02 reacts, OH reacts, you get 0.02 of X minus and 0.02 of extra water. Water is already in excess, so I don't worry about additional 0.02. But however, we will have to take into account that 0.02 of X minus that you get because of the reaction of 0.02 molar OH to HX. So now our new concentration, let's write down the new concentration of HX and X minus. HX, that's after the addition of the base, potassium hydroxide, is now 0.08, and acetate ion, 0.13 plus 0.02 is 0.15. So that's 0.15. Now we can use these quantities in Henderson-Hasselbalch expression to get pH value. So let's now write down the pH expression. So pH equals to minus log of Ka, and we know the Ka value, 1.8 times 10 to the negative 5. The Ka value for acetic acid, HX, plus log of conjugate base over conjugate acid, which is 0.15 molar by 0.08. Now let's see what you got. The first part we got 4.74, and the second part we got 0.27, and this gives us 5.01. So that's the answer to this question. That means after you add 0.02 molar potassium hydroxide, the new pH is now 5.01.